Okay, let's do 13.13. The radionuclide carbon 11 decays according to an equation, and they've given you the half-life period also, but don't worry about it. But I mean, if you just look at the problem, the half-life period is given to be 20.3 minutes. So in about half an hour it will become half. About 15 minutes it will become, in 20 minutes it will become half. So that's what it is. Okay, so other than that, we'll just get on to the problem. The maximum energy of the emitted positron is 0.96 mega electron volt. Then they've given you the mass values. Then calculate Q and compare it with the maximum energy of the positron emitted. Okay, so this is what it is. The nuclear reaction is this. This is 13.13. So you have carbon 11, 6, 11 that decays into boron 5, 11 by emitting a positron. E, obviously a positron will always be accompanied by a neutrino. So this is the reaction. So the given values are these. The mass of carbon atom, okay, 6 is given to be 11.011434 atomic mass units, and boron 511 is given to be 11.009305 atomic mass units. Okay, so this is the mass. Okay, and what else is given? The emitted positron energy. Okay, this is E plus, right? This emitted positron energy is E plus. Energy, the kinetic energy of positron, E plus, is given to be 0.96 mega electron volt. Okay, this is information given. And what is asked, calculate Q and compare it with the maximum energy of the positron emitted. They want you to calculate Q. Okay, generally what we do, you take this, okay, and then you take the mass of, okay, what has happened is that, so you have this mass, that's the parent mass, then you have mass of boron, mass of positron, and mass of neutrino. You combine, then you find the difference, you find the mass defect, and convert that into energy. So multiply that by c squared if the mass is in kg, or multiply that with 931 if the mass is in atomic mass units to find the energy in mega electron volt. So that's how you do it. Okay, but in this case there are two things you need to remember. One, the mass of neutrino is negligible. You can forget it. Even for this, you can kind of forget it. The reason is that if this has very low mass, electron or positron, very low mass, the mass of neutrino or antineutrino is very, 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 very small. Much smaller than even, much smaller than even electron. So it's very difficult to detect them. Okay. So you can ignore this mass. Let's focus on the other two masses. So the masses that are important here are the mass of boron and the mass of the positron. The mass of positron is the mass of electron. As I said, the only difference is the charge. Everything else is the same. The mass is the same. It's matter-antimatter pair. Positron and electron are. Okay, so that is one thing that you have to remember. The second thing you have to remember is there is a slight difference here between what we discussed before and what we're discussing now. And in the previous problems, we're dealing with alpha particles. Okay. So alpha particles are heavy, right, compared to electron. Okay. So what is this? C11 and B11, these are all atomic masses. They are not nuclear masses. They are atomic masses. It's atomic mass number, which means that these involve the mass of the electrons also in the atom. But in the previous cases, we kind of ignored them. It's because we're dealing with heavy particle, alpha particle. So when you're talking about masses of alpha particles, then you can kind of ignore the mass of the electron and stuff. But in this case, you can do it. Why? Because what is emitted is positron, and positron is nothing but an electron. It's like losing an electron, okay, with a positive charge. So you have to consider the masses of the electrons in the atom too. Previously, alpha particle was lost. Now, a positron is lost. So when alpha particle was lost, you didn't bother about the electronic mass. But when a positron is lost, you have to be bothered about the electronic mass. So you have to be careful about it. Okay. Now, where is the mass defect taking place? It's taking place in the nucleus. Okay, so you have to worry about the mass of the nucleus. What happens to the nucleus? Okay, so what is given here is mass of the atom. In the previous examples also the mass of the atom was given. But in the previous examples, the previous problems, you are dealing with alpha particles. There is a lot of mass involved. But here only a little bit of mass involved, so you have to be careful. Let's get back. So what is this? Mass defect. Mass defect is going to be equal. Where is it going to happen? It's going to happen only at the nuclear level. Okay. So that which means that the mass of this nucleus, I'll say nuclear mass, right? Okay. I'll say mass of carbon nucleus minus mass of boron nucleus, okay, then minus this stuff, mass of positron. So that's the mass defect. I'm going to ignore the mass of neutrino, okay, because it's so small. Forget that. It's like ignoring the mass of electrons when you deal with alpha particles. You will ignore the mass of neutrino when you're dealing with electron or positron. Okay, so it's like that. So this is the mass defect. Well, what is given? You have been given this mass, right? So what is that mass? This is atomic mass. So mass of carbon minus, what should you have? Mass of carbon minus, how many electrons are there? There are 6 electrons. Okay? So you need to subtract the mass of 6 electrons from here. So 6 into mass of electron is actually the mass of the nucleus. So from this number you have to subtract the mass of 6 electrons to get this number. Because delta M takes place only in the nucleus. Okay, that's it. Again, what is this mass of nucleus? That's going to be mass of boron minus how many? 5, right? Okay, so that's going to be into 5 mass of electron. Then minus mass of electron, actually this is. Mass of positron is the same as the mass of electron. So this is what you get. So when I do this, so what I'm going to get now? This is going to be equal to mass of carbon. This is 6 minus 6. Now you get, okay, I'll do this. So it's like this, right? Minus of this. Or I'll leave it like that, better. Okay, leave it like that. So this is mass of carbon. Then what have we got here? Then minus mass of boron. Now let's worry about the electrons now. See, this is got minus 6 here. You will get plus 5, then minus 1. So minus 7 plus 5. So you will get minus 2 again. So that is going to be the delta M. Okay. Why are you doing it like this? It's because you are dealing with positrons. If you are dealing with alpha particles, you can straight away use, because it's not much of it, the masses involved are much bigger than the electronic mass. So you can take this to be the mass of the nucleus itself in most cases. I mean, if you can subtract the number of electrons, that's fine, but usually it will be an overkill. Okay. But this is how you have to do it. So you got this now. So delta M is what you got here. But once you get this, then what is Q? Now Q is simply this delta M into 931 mega electron volt. Simple. Got it? So you will get some number for this. So this is MC is this 11.00143. MB is this atomic mass. You are getting atomic mass minus 2 times the mass of electron. So what is the mass of electron? I'll write that too. Okay, the mass of electron is equal to 0.00055 unit, right? So twice that. So subtract that also, then you get this. So this delta. Okay, you will get some value, I suppose. Okay, then you compare that with the energy of this one, the positron emitter. The positron is then kind of 0.96 mega electron volt, and if you do this, if I do this, I'm supposed to get I'm supposed to get again 0.961 mega electron. So I'm going to get 0.961 mega electron volt. It's understandable. So all the energy is going to be with the positron emitter, and the energy of this, this neutron can be ignored because it has a very low mass. So almost all the energy will be with this one at one end. When you do it, the important thing is you must have minus 2 ME here. If you don't have that here, then you will have a different number there. If you straight away use this MC minus MB into 9.931 mega electron volt, then you will have a different number. The important thing is that you account for the electrons also in this. Okay, so that's what you get. Hope this is clear to you. Let's do 13.14. This is similar to 13.13 that we just did. The nucleus neon 23 decays by beta negative emission. Write down the beta decay equation and determine the maximum kinetic energy of the electrons emitted. So given that, they've given something. Okay, they've given neon and also they've given sodium, but I think there is some problem with the sodium number. Let's say that we'll do that. So basically, like you have neon and then it undergoes beta negative emission. So they want you to find the kinetic energy of the electron emitter. Simple, okay. So you got 13.14. So you have neon 23. So you got 10 Ne23. Okay. This undergoes beta negative decay, right? So it's going to be beta negative decay. So what I'm going to get now? It's going to give me first beta negative, meaning I'm going to get an electron. Okay, and if you get an electron, obviously I'm going to get an anti-neutron along with it. So those two appear in pairs. So that's how it is. So this is, what does it mean? It's going to be minus 1, 0, right? So that will give me sodium 11 and then 23. This is minus 1, 11 become 10. So by releasing an electron and an anti-neutrino particle, one of the neutrons in the neon nucleus has become a proton. So that's what it means. Okay. So you get that. So what have they given? They have given you the mass of neon 1023 is 22.994466, and then the mass of sodium 23 is 22 point. They've given 0.89770 this atomic mass unit. I doubt this. This must be 9. It cannot be 0. You can't have such a big difference. Okay, like, which is like 1 unit means that you are going to get 931 mega electron volt. Okay, so almost coming out. Okay, so this must be 0.98. Cannot be 0. I think there is the book is wrong in that. So what you have to do is, well, you have to find delta M. But what is delta M? Delta M is going to be the mass of neon nucleus, okay, minus the mass of, what is that, sodium nucleus, right, and then we lost an electron, right, then minus the mass of electron. I'm going to ignore antineutrino. Why? Because you see the electron emission is taking place. That is why you need to be careful about this. You have to take nuclear mass. What is given here is atomic mass all the time. But the moment you have beta, then this is what you should be doing. Okay. So the nuclear mass, what would you do? So the mass of neon as given here, and minus how many electrons? We have 10 electrons now. 10 mass of electron, that's the first one. Then minus, what do you get? Mass of sodium. So this is going to be mass of sodium atom minus how many electrons? 11 electrons. 11 mass of electron. Okay. And then minus mass of this electron. So this is what it is. So this will result in mass of neon minus mass of sodium atom, mass of neon atom minus mass of sodium atom. Then what's going to happen? You got minus 10 here, we got plus 11, and then what we got here? Here minus 1. So minus 11 plus 11, 0. So this delta M, in this case, we are safe. Okay, because that will be 0. So you can straight away subtract this. But actually, you are not dealing with nuclear thing. I want you to understand that. Okay, so I hope this is clear to you. So once you get this delta M, then Q can be obtained. What is Q? Q is delta M into 931 mega electron volt. So you get some number for that. This difference multiplied by 931 mega electron volt will give you Q. So once you get that Q, what would be the kinetic energy of the electrons emitted? I mean, the electron will have all the kinetic energy because sodium will hardly move. The mass is so big that this will rarely get anything. You remember that, right? So the kinetic energy of anything is going to be equal to Q times mass 1 by M1 plus M2. Okay, so this is what it is. We saw it. It will be so small. The mass 1 would be the mass of, if you want electronic kinetic energy, M1 would be that of sodium itself, sodium. And here, sodium mass plus electronic mass. Electronic mass can be ignored. So M1 by M1, so it will effectively result in Q. All the kinetic energy would be with the electron. It's emitted. Just like all the kinetic energy was with the positron in the previous case, almost all the kinetic energy will do with the electron this time. Okay. So this is how you do this problem. Okay. And problem 13.15. The problem 13.15. Let's say this is equal to Q in this case. Problem 13.15. So they've given you two equations, two reactions. They ask you to figure out what are which one is exothermic and which other is endothermic. Okay, you know that exothermic meaning that it has to release energy. Okay, so if the mass of the reactants, okay, is greater than the mass of the products, then clearly the excess mass will get converted into energy and be released. Okay. If the mass of the products is more than the mass of the reactants, then you have to provide energy so that the energy is going to be converted into mass for the products. So then that will be endothermic. Okay, so just sum up the masses and then see which side is greater in this example, in this exercise problem, and if the reactant's mass is more than the product mass, then it must be exothermic. If the reactant mass is less than the product mass, then it has to be endothermic. You have to supply energy. Okay, so that's how it is. 13.15. It's a very simple problem if you understand this idea. Okay. 13.16 is also the same. We'll discuss 13.15 and 13.16 is almost similar. Suppose we think of fission of iron 56 nucleus into two equal fragments, aluminum 28. Is the fission energetically possible? Argue by working out Q of the process. Given M is 55.93494 and L is 27.9819 U. The same idea. Okay, so let's say you have iron here, iron 56. Okay, 26 and then 56. They say that it is breaking into aluminum, two aluminum. Okay, and they're asking if this is possible because you have 13 here and then 28 here. So twice will be two aluminum atoms, one iron atom becoming two aluminum atoms. No, is it possible? I should say one iron nucleus becoming two aluminum nuclei. Is it possible? Yeah, if you look at this, twice this will be 26 and then twice this will be 56. It seems possible. Okay, let's see if that is possible. What is the mass of this iron? Iron is, okay, mass of iron 56.26 is given as 55.934. 0.93494 atomic mass units, and the mass of aluminum 28 is equal to 27.98191. Okay, so there will be two of them, right? So I mean, there should be two of them basically. One more aluminum 28. They're asking if this is possible. So then, if you multiply this by 2, and I'll get some number. So what that number would be? We will do this now. So this is going to be equal to 218 the 3 in 1 9 point, okay, and this will be 55. Note here, this is 55.963 here it's 55.93. So this mass, the parent mass, is less than the sum of the daughters. So this cannot happen spontaneously. This won't happen spontaneously. Okay, so this cannot happen. So that's the idea. That is 13.16. 13.17 is a very simple problem again. 13.17. The fission properties of plutonium-239 are very similar to those of uranium-92, uranium-235 I should say. The average energy released per fission is 180 megaelectron volt. So then how much energy in megaelectron volt is released if all the atoms in 1 kg of pure plutonium undergo fission? 239. So what they're saying is that plutonium is similar to uranium in terms of the energy that it gives. So you have plutonium 94 239. Okay, so this is what you got. So this gives you, when it undergoes this nuclear fission, then it gives you 180 mega electron volt of energy. So now they're asking you to figure out how much energy in mega electron volt is released if all the atoms in 1 kg of pure plutonium undergo fission. Okay, that depends on the number of atoms in 1 kg, right? So this is the one atom, 180 megaelectron volt. So you have 1 kg of plutonium, so you need to figure out how many atoms and how many nuclei are there in 1 kg. So there will be one atom per, one nucleus per atom. So if I figure out how many atoms are there in 1 kg of plutonium, then you will be able to figure out how many nuclei are there. Then multiply that with 180, then you will get it. So it's going to be Avogadro number, right? So 239 grams will contain 6.022 into 10 power 23 nuclei atoms. So now you got 1 kg, so that's going to be equal to 6.022 into 10 power 23 by 239 into 1000. So 4 times that. Okay, so 4 times this number will get 4 times, more than 4 times. Avogadro number. That's what we will get. So you find the number of atoms in 1 kg. Okay, in 1 kg, you get this. So per atom or per nucleus is what you get. So the energy is Q, it's going to be equal to this number into 180 mega electron volt. So it's a very simple problem to do. Okay, and then 13.18 uses half-life period and stuff, so let me not do that. Let me move on to 13.19. Well, 13.19 is similar to 13.17. How long can an electric lamp of 100 watt be kept glowing by fusion of 2 kg of deuterium? Take the fusion reaction as this. So this is 13.19. So the fusion reaction is this. You got 1 H2 deuterium that combines with another deuterium to give you helium-3 plus a neutron plus 3.27 mega electron volt energy. So this is the energy that is coming out of this fusion reaction. Okay, and now what is asked? You have 2 kg of deuterium. Fine. So you have 2 kg of deuterium. and you have a lamp which is 100 watts. So they say like how long can it be kept operating? Well, that depends on the energy that is released in this, right? So 2 deuterium can produce this 3.27 mega electron volt of energy. Then you need to see how many deuterium are there in 2 kg. Okay? So very simply, 2 grams, right? This is 2, right? So 2 grams will contain 6.022 into 10 power 23 deuterium nuclei. Then 2 kg, 2000 grams will contain, and 6.022 into 10 power 23 by 2 into 2000, you go here, so you effectively get 6.022 into 10 power 26 nuclei atoms. So many, so your N is going to be so many. Okay, but how many reactions are possible for this? You can have only n by 2 reactions, because for one reaction you require 2. So you have so many. So how many reactions are possible? N by 2 reactions are possible. Number of reactions possible is equal to n by 2. And then per reaction you are going to get 3.27 mega electron volt. So Q, total Q is going to be equal to n by 2 into 3.27 mega electron volt. So you get this. Okay. Now you get this converted into some joules. Okay, energy in joules. You get that. So this is the amount of energy available when the whole material undergoes fusion. This is the amount of energy that will be released. But what does your bulb do? It takes 100 watts. That is 100 joules per second. Then you figure out how many joules are here. And per second, 100 joules is going to be taken from this. So, how many seconds this energy can be used by your bulb? So, that is how long the bulb will glow when you do this. Okay, I hope you understand this. What have we done here? We have figured out how many nuclei are there in 2 kg of neutron. And we know that 2 nuclei are required for one reaction. So if n is the number of nuclei available, then n by 2 reactions are possible. So for each reaction you are going to get 3.27 mega electron volt. So the amount of energy released will be n by 2 into 3.27. So that's the amount of energy you will get. But that is a mega electron volt. So they convert that into joules. So many joules are available for you. Now you look at your bulb. It takes 100 joules per second. So many joules are there. So for how many seconds can the bulb use this energy? And that's the duration. Okay, that's a very simple problem. Okay, we'll do problem 13.20. Calculate the height of the potential barrier for a head-on collision of 2 deuterons. So there is a head-on collision of 2 deuterons, and they want you to find the potential barrier. So what it means is that the amount of energy you need to give, so that they come and hit each other. So there is one deuteron, so you need to give another, you have to take another deuteron and throw it with such velocity that it is able to go and hit it. Why is it such a big deal? Because you see that they are positively charged. Okay, so when they go and hit each other, there would be a Coulomb repulsion, right? The electrostatic repulsive force will always act. So when you throw this deuteron, so that's going to be slowed down by the other deuteron. But this should have enough speed and enough velocity, kinetic energy to go and hit it. Okay. If it doesn't have enough energy, then you can't do that. Okay. It will be stopped before it reaches here, and then it will return. There won't be any collision. So it must have enough energy to go there. Okay. So what would be that energy? So that is the potential barrier. Okay. You can calculate the potential barrier of that. Okay. The hint is also given. The height of the potential barrier is given by the Coulomb repulsion between the two deuterons when they just touch each other. Assume that they can be taken as hard spheres of radius 2 femtometers. Okay, so this was 1320. So what has to happen is that there is a deuteron and you throw another deuteron in such a way that it comes and hits you. So what's the minimum energy that you should throw it with so that it comes and hits you? So what they say is that the radius, this is r and this is r. So this radius is 2 femtometers. So that is equal to 2 into 10 power minus 15 meters. So this is 2 and this is 4 femtometers. Well, how can you do this? How can you calculate it? It's a very simple problem. It comes down to what you found or what you came across in lesson number 2, electric potential, right? Because you're going to do work against this. Yeah, as you throw it, this deuteron, you have to do work against it, and then it has to come here. So what's the amount of work you have to do? So that's the amount of energy you need to give. So it comes here, right? So I can treat this. So this is also positive. This is also positive. Now the deuteron will have one proton, this will also have one proton, this is also positive. And now, if I take this deuteron, okay, let's say this has certain charge, E is a charge, E positive is a charge, right? And what would be the potential at this distance? Well, I can assume that the charge is concentrated at the center. And here also the charge is concentrated at the center. Okay. So now the distance is 4 femtometer. What would be the potential? That is, what is the work you have to do to bring it from there to here, effectively, right? So because you are going to have this here. What is the work you need to do? And that is the energy it should possess. So that's the potential barrier. You need to give more energy than that for it to come and hit. You should provide at least this amount of energy so that it comes and touches this. Anything more than that will go. Okay. Because otherwise it's going to keep pushing it, right? Anything less than that, it won't even touch. It will come, it will slow down, it will go back. And if you throw it faster, then it will come and then touch here and then go back. And if you throw it even faster, it will come and hit it with a certain speed. Okay, so what's the minimum you need to do? That's the, so that it comes and touches. You get a head-on collision. That's the question. So what you need to do? Well, if you find the potential V at this point due to this charge, and if you multiply this charge, then that is equal to the work done. That is the amount of energy that it should have to come here, right? So what does this? All the kinetic energy you give would become potential energy here, right? So the potential energy U is equal to V into Q. That's what you know. So what's the? So all the kinetic energy you are given would become potential here. So that's the minimum you should give. Anything more, it will come and hit it. Okay. So this is the minimum you get. Okay. So this is equal to, what is V due to this? Well, this is KQ by this distance R. I'll call this as R. Okay. And this KQ by R that's V, this one, into that Q, the other Q. Okay, so this would be 9 into 10 power 9 K, then Q would be 1.6 into 10 power minus 19. And what is R? This is 2 femtometers and this is 2 femtometers, 4 femtometers. 4 into 10 power minus 15 into 1.6 into 10 power minus 19 joules. And if you were to convert that into into electron volts, then what would I do? I'll divide that by 1.6 into 10 power minus 19. Now this is going to become electron volt, no longer joule. So this will cancel with this, and this 4 will become, this will become 0.4, 1.6, 0.4. So you get this. So 9 into 0.4 will become 3.6 into 10 power minus 10, 9 minus 19 minus 10, then 10 power minus 15 you take, and it will become into 10 power 15 electron volt. So that gives you 3.6 into 10 power 5 electron volt, and that gives you 360 kilo electron volt. Okay. So if I throw it with this amount of energy, if it had that kind of kinetic energy in the beginning, then it will come and touch this, come and touch that. Anything more, it will collide. It will have a collision there. So that is how you do this problem. You are bringing two nuclei together. Okay, so that is how we do this problem. You see, your last lesson has a problem that connects it with the first lesson. Okay, 13.21. From the relation R is equal to R naught A to the power 1 by 3, where R naught is a constant and A is the mass number of nucleus, show that the nuclear matter density is nearly constant, which is independent of A. We've done that already. Okay, we've done that in the class, one of the lectures. Okay, so it doesn't change. So we've done it already. So I'm not going to do it now. Okay, the last problem that we'd attempt is 13.22. 13.22. For the beta plus emission, the positron emission from a nucleus, there is another competing process known as electron capture, which means electron from an inner orbit, say the K shell, is captured by the nucleus and a neutrino is emitted. So they've given you the reaction. Show that if beta plus emission is energetically allowed, electron capture is necessarily allowed, but not vice versa. Okay. If beta plus emission is energetically allowed, electron capture is necessarily allowed, but not vice versa. What it means is that if beta plus emission can happen, then electron capture can happen. But if electron capture can happen, it does not mean that beta plus emission can happen. So that is what they mean. Okay, so we'll do that. So there are two things that we talk about. We talk about beta plus decay, and the other one is electron capture. When is electron captured? Sometimes it is possible. Let's say 13.22. So you have the nucleus here, and then electrons orbit around the nucleus, and sometimes if an electron in the inner orbit, if it gets jolted out of its place, then it can be captured by the nucleus. For different reasons, an electron can be can be pushed out of the orbit, and once it gets pushed out, then it can be captured by this nucleus. So that's called as electron capture. Okay, that's the electron capture. So clearly, what happens when the electron is captured? When the electron is captured, then one of the protons will become a neutron. Okay, with additional energy, obviously. and become neutron. Because the neutron requires more mass than just the proton and the electron. So, the electron, we need some more mass to make a neutron, right? So that will come from the kinetic energy of the electron. So let's not get into that now. Okay. So what happens is that a proton can capture an electron, then become a neutron. So that is called as the electron capture. The electron in the inner orbits may be captured under certain circumstances. That can happen. If the electron gains more energy and gets jolted out of the orbit, then this can happen. Then the element becomes a different element. Okay? So that is one process. And what's the other process? That's the beta positive emission. So the positron is emitted. When the positron is emitted, then a proton can become a neutron. Okay, so these are the two processes which give the same result. Okay. So now let's see how things go on from here. Okay. First, let me talk about beta positive. So what happens here? In that case, you have an element X, and that has atomic number Z and then the mass number A. Okay. So what happens is that there is a positron emission, so you get E positive along with it a neutron. And then what happens here, positron is gone, so one is gone, so you have another element with another element that gives you Z minus 1 and E. There's no change in here. There's no mass, not much of a mass change that's happening here, but then the atomic number changes. So this is beta positive. So that is what happens. Okay. And the other process, the electron capture process, is this. So you have this element X, okay, then ZA. Now you capture an electron minus, and then what happens is that you become Y, and that is Z minus 1, because it's minus 1, and then you get A, and along with it you get a neutron. Okay, so this is the electron capture process. Electron capture. Notice that in both the process, you have this. The element, changes. X becomes Y with the same atomic number and then the mass number. Okay. So now let us see. Let's look at it from the energy perspective. So what will be the energy released in the first process? It's going to be delta mc squared, right? So what is the delta m for this? So the delta m for that would be, so that's first process, 1 beta positive. What's my delta m? My delta m is going to be equal to this mass minus these masses, right? So what is this mass? No, well, this is atomic mass number. So I get mx. This is the atomic mass minus, I have to get the nuclear mass, right? Mx minus Z into mass of the electron. That's my nuclear mass. Okay? Atomic mass minus number of electrons into mass of electron. Okay, this is what you start with. Then what happens is then you give out these, right? So that becomes minus, what is this? Nuclear mass of that. What's the nuclear mass of that? So the mass of Y, atomic mass of Y, minus, how many electrons do you have? Z minus 1 electrons, right? Z minus 1 electrons now. Mass of electron. So that will be the nuclear mass of this. Then what you get here? Then minus this mass of electron. Okay? So they were done it already in one of the previous exercises, problems. So when you do this, then what you get here is mx, mass of atomic mass, then you get minus zme, and then minus my, and then minus minus plus, right? Plus zme, minus minus plus minus me, and then minus this me. I'll probably have a 0 so that you have no confusion. Okay, so this and this will cancel. So you get atomic mass x minus atomic mass y minus 2me. So that is the delta M. For this. Then what is the energy? This will be into c squared. That's the energy, right? That's what it is. So I'll get Q, I'll call this as process 1. Q1 is equal to delta M c squared, which is equal to mx minus my minus 2me into c squared. Well, let's do the same thing for this one. Electron capture, we call it as EC. So, what is the delta M? So, delta M is going to be equal to this mass, combined mass, minus this mass. Yeah, I can ignore this mass, right? Yeah, this mass and this one. So, what is that mass then? Well, the atomic, I have got the nuclear mass, right? So first let me get the nuclear mass of this. That would be same atomic mass minus z times mass of electron plus mass of electron. Okay, that is so this becomes this, right? So then minus the nuclear mass of this, that would be mass, atomic mass of y minus z minus 1 electronic mass. I can ignore that. That's it. So what I'm going to get here? I'm going to get mx, atomic mass of x, minus zme plus me, then minus my, then minus minus plus z me minus 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 me. So this cancels with this cancels with this. So this simply, for the electron capture, delta M is simply mx, atomic mass minus atomic mass. That's delta M. Okay, and this is the second part. Then what's the energy here? So Q2 is equal to delta M c squared. That will be mx minus my to c squared. Okay. So note this. This Q1 is mx minus my minus 2me c squared. Suppose this is positive. There is a positive energy it's coming out. Okay, and beta plus energy is positive. And this is positive. This has to be necessarily positive. Because mx minus my minus 2me itself is positive. So mx minus my must be positive. So if this is positive, this has to be positive. Okay. So if this can happen, this can also happen. This can happen. But if this is positive, can I say this is positive? No. This can be positive, but this may still be negative because this may be, this mx minus my may still be less than this me, 2me. So in that case it can be negative, it can still be negative. So if this happens, this can happen. But if this happens, you cannot say that this can happen spontaneously. So that is the inference from this. So that's what the question is. So from the energy considerations, you prove that when this happens, this also can happen. But this happens, you can say this will happen. Hope this is clear to you. And with that, we end our discussion on the problems in this lesson. If you have any questions, get back to me. And with this, the syllabus, your +2 syllabus is over. All the best to you.